Welcome, ladies and gentlemen, to Calculus BC. In today's episode, we will be continuing our journey through polar graphing, and we will investigate some more complicated looking graphs. And so in the first example, I'm going to graph this thing called r equals 2 plus 2 cos theta. Now in the last episode, I spoke about graphing things rectangularly first, and then graphing things polarly, especially in the beginning, and especially because we don't touch on polar that much. It's important to know how these things look. Eventually, you'll start to recognize these things more quickly. Like how you would recognize a parabola or an exponential. But for now, let's go ahead and investigate what this guy's going to look like. So, from here, let's take a look at 2 plus 2 cos theta. So let's go ahead and draw my line right here. That's very straight because I was holding the shift button. Okay, so from here, our vertical shift is 2. Right, we are up 2 because of our vertical shift here. Now, our amplitude is 2, which means we're going to go as far high as 4 and as down low as 0. Now, cosine, and again, I'm going to go and graph, just like I talked about in the last video, I'm going to go and graph on 0 to 2 pi, like that, where 2 pi will end the function. Pi will be here, pi over 2, and then 3 pi over 2. Now, the way this works is this graph here is unique among all of the other polar graphs, because if you notice, and we talked about this in the last video, my graph is always above the x-axis or always above the theta axis, which means my r values are always positive, which means we are consistently advancing. We are consistently advancing on this graph here. So we are never going to be moving backwards depending on how we're facing. We're always moving forward, which makes this graph advantageously easy, if that's not a redundant statement right there. So from here, let's go and just figure out our points. So it looks like when my angle value is 0, my radius value is 4. So I will face 0 and go out 1, 2, 3, 4 right here. And then, as I advance towards pi over 2, my radius value gets smaller. It moves towards the value of 2. So at pi over 2, I can say that my radius value is 2. So 1, 2, like this. So I can actually arc myself in this way and connect there. Now from here, when I'm facing pi, my radius value is 0, which puts me here. And then at 3 pi over 2, when I'm facing 3 pi over 2, I will be advancing to 2 radius out. So that'll be out to here. Now what happens is that the way these guys connect is he extends a little bit beyond the 0. And again, he's still advancing, right? Still advancing this way, and then comes back in and forms almost this heart-shaped figure. This is what is known as a cardioid. Oops. For the very reason that it looks like a heart. Now, I know what you're thinking. How did I know to go beyond 0 right here and beyond 0 right here? Well, what's up with that? Well, if you plug in a number like 2 pi over 3, which is in between the pi over 2 and pi. So if you say, all right, r equals 2 plus 2 cos 2 pi over 3, right? And so from here, what you get is cosine of 2 pi over 3 is negative 1/2, right? So negative 1/2 times 2 and then plus 2. So what you get is you get 2 minus 1, which is positive 1. Your radial value is going out by positive 1 when you're facing 2 pi over 3, which is why I advanced out 1 radius. And notice how my graph hits that radius unit of 1. It'll happen the same way out here at 4 pi over 3, I'll hit a radius value of 1. If you want to do the math, you can go ahead and check. And so, how far out does it go? It's not super duper mission critical, but just to know that the general shape of the cardioid kind of looks like this. And then, of course, I should change colors for that. Drawing the arrows of how it grows is really important. And so it's going to grow out like this. So that's your cardioid. Of course, it will vary with sine. When it comes to sine, it will be facing up or down. Cosine will be facing left or right in terms of your cardioid. So, whoa, you are still there from the last video. We don't want you. Okay, let's go ahead and take a look at the next example here. So we've got 4, r equals 2 minus 4 sine theta. And so, again, I'm going to go ahead and graph this rectangularly first. I'll go and graph him rectangularly first. Here's my vertical axis. Here's my horizontal axis. And so, again, my vertical shift is up by 2. Now, because my amplitude is 4, I'm going to go as far up as 6 and as far down as -2, and sine is upside down in large part because of the negative. So from here, sine will start at the 2, at the centerpiece, go down to its minimum, go up to its maximum, and come down. And so from here, this is 2 pi, pi over 2, and 3 pi over 2. Now, one thing that makes this graph unique is the idea that you are only retreating for a small smidge of time, which is going to be right here and right here. Whenever you have a situation that looks like this, it's important to know that you want to set your equation equal to 0 so that you can find out where your angles are equal to 0. So that if you do a little bit of algebra, you'll get 1/2 equaling sine theta. And what you get is theta equaling pi over 6 and 5 pi over 6. That's where these things are. So why is this important? It's because I know that between pi over 6 and 5 pi over 6, my radius is retreating. Everywhere else, it is advancing. So let's see how that manifests itself in our polar plane right here. So again, when my angle value is 0, my radius value is 2. So I'm going to go out to here. This is 2. And I suppose I should have zoomed in a little bit more on this thing. As I advance towards pi over 6, my radial value will get smaller. So it's going to come in. It's going to be tangent to the pi over 6 at 0 right here. It's going to jump in like this. And then once I blast through pi over 6 and I start facing pi over 2, at pi over 2, my radial value is 2, but it's retreating. So it's going to go down 1, 2 values like this. And it's going to, remember, I'm facing pi over 2. My Lego character is facing up, but he's going to be moving backwards. He's going to be moonwalking back into this area. And then, as you approach the 5 pi over 6, he's going to be moving in towards 0. So from here, as you spin towards 5 pi over 6, remember, you're facing 5 pi over 6, but your retreating values are getting closer to 0. You're doing less retreating. And then, as you spin towards pi, you will advance towards 2. You will advance towards 2. Sorry, that was misaligned. You will advance towards the 2 once again. And then what you'll get is when you move towards 3 pi over 2, you will advance towards 6. So that's 1, 2, 3, 4, 5, 6 out like this. You will advance towards 6, and then you will come back towards the 2. And there you have it. That is your next graph. So again, I will go ahead and draw the arrows in. Now, if you notice the little loop on the inside, this is what is known as a limacon. And it has a little accented character right there. It is a French word, limacon. And so when we find the area of a limacon, I'm hoping you guys will see this now. It's easy to overlap this little donut hole in here. You don't want to, double the donuts is good, as long as you are, young and healthy and not old like me. But you don't want to double up in this area, and we will deal with that when we talk about integration of polar functions. So that is your next example. Let's move on to the last example here. I'm going to go and pause and clear off the board. And here comes our last example. This is what is known as a lemniscate, and I will write it down when we're done graphing it. One of the things that's very noteworthy about the lemniscate is that the outputs must always be positive. And the reason why is because the outputs are always being squared. So the outputs are always going to be positive, so make sure we keep this in mind when we go to graph the lemniscate on our rectangular and our polar. And one of the consequences of the outputs always being positive is that the radius is always advancing. I actually really prefer when the radius is always advancing. I don't have to think about forward and backward motion. I think it's a little too complicated for me. So before I go and graph this thing in polar form, or in rectangular form, I'll go and take the square root of both sides. That's going to be the square root of 9 sine 2 theta. Now, before I even do anything with this, I can actually see him as the square root of 9 times the square root of sine 2 theta, giving me 3 rad sine 2 theta. And now from here, how that helps me in the rectangular graph is it helps me see this as a regular sine. Now, for the moment, I'm going to ignore the square root function. I'm going to go and ignore it. I'm going to just pretend that it's not there. I'm going to go and graph a regular sine function here, and then I will deal with the square root accordingly. So 1 sine, 2 sine right there. And again, I'm always graphing on a period of 0 to 2 pi, because that is one full cycle of the unit circle. Now, just like we did with sine in the first video, I will go ahead and put in all of the humps and the underlumps in terms of their radian value. So 5 pi over 4 and 7 pi over 4. Now, remember, I said I was going to ignore the square root, at least for the beginning. Now I'm going to take them into account. Remember, the outputs are always positive, which means the radius has no capacity to be a negative value. So what I'm really looking at is I'm really just looking at the top portion of the graph. I'm really just looking at the top portion of the graph. So how does that help me with the polar version of this graph? Well, let's go ahead and translate him. So from here, at 0, when my angle value is 0, my radian value is 0. Pi over 4, I have a radius of 3, so 1, 2, 3. I'm hoping that we're able to kind of see this a little bit faster now. And I'm going to kind of cycle out to get there. So just like I did with the first flower, it almost looks, it's reminiscent of the flower graph, except you'll notice a change. Because now I'm no longer going into the negative plane. My next facing point is pi. And when I'm at pi, my radial value is 0. I advance towards 5 pi over 4, going 3 radii out, so 1, 2, 3. And I advance going out and then coming back in at 3 pi over 2. So when it comes to the lemniscate graph, this one here, it will cycle out like this and almost cusp down at 0 and then do that. So it's not. So it doesn't form like an infinity sign. It doesn't do this. What it does is it goes like this, and then this. So it's almost like forming a peanut of sorts, or a helicopter's propeller. And so there you have it. That is the lemniscate right there. Lemniscate. And those are your 5 basic polar graphs. So as always, please know that they're going to change depending on whether or not you're dealing with sine or cosine. The frequency of the function is going to depend on how many propellers you're going to have on the flower and stuff like that. So in your homework, you will deal with those. As always, please leave comments or questions in the comments area, and I will see you when it comes to the calculus episode of Polar.